move to the third talk. So the title is CECI, Compact Embedding CLuster Index for Scalable Subgraph Matching. Okay, so you're also doing the subgraph matching. The presenter is
Vivek.
Okay, you introduce.
Hi. Thank you for the introduction. My name is Vivek, and my project's name is CECI. It stands for Compact Embedding CLuster Index. Hopefully, you'll understand what it means at the end of the presentation. So, similar to the last talk, we're trying to solve the problem of subgraph matching, which basically includes listing all the isomorphic embedding of given query graph in a large data graph. I'm not going to go over the detail as he has already explained in much detailed extent. Thank you for making my job easier. So we have a data graph and we have a query graph. And here's one of the isomorphic embedding we can find for a given query graph in that data graph. And here's another one. It has application in many areas, including but not limited to bioinformatics, cheminformatics, social networks, cybersecurity, or wherever you have to search for a pattern in a large data graph. But utilizing this on the real-world scale data graph size is really hard. Since this is an NP-hard problem, it tends to scale exponentially with the increasing data and query graph size. So normally people tend to throw the parallel computation to solve the problem. But making subgraph matching parallel comes with several challenges, including the problem of efficient workload decomposition. And then there is always the candidate verification overhead, as the previous talk has already talked in much detail. And we always have a good old workload imbalance in any graph algorithm. So I'm going to go in detail about each of these issues a little bit later. Just to reiterate what he has already explained, I'm going to show you how the simple subgraph matching works. We normally choose a root query node from where we start our matching. And then normally we define a spanning tree. For the simplicity, I have chosen BFS to illustrate everything, but there has been extensive amount of research on the different options of spanning trees. And similarly, for matching order, there has been many research, including the last talk. So once you get the matching order, starting node, and then the skeleton of the query, you basically start from the starting node, match one data vertex to the starting node, and then you move to next vertex in matching order, and so on, until you reach the last node on the query graph. And then that backtracking path from root to leaf basically constitutes one embedding. Let's look at the issues while we face when we parallelize the subgraph matching. The first obvious problem is how we decompose the data into multiple workers. Normally, people tend to follow one of two approaches. They go for query graph decomposition, where they send individual edges or the node of the query graph to different worker, ask them to collect the candidates independently, and then bring all the candidates to some global server, and then do the join. The obvious problem with this one is when you collect the candidate with individual component, you lack the global context. So you naturally tend to collect much more false positives, and that will make your join cardinality really, really, really large. And the other way people go is decomposing the data graph. You basically form multiple partitions of the data graph, and then send one partition to the one worker and ask them to find all the matches of the query on that partition. In addition to the obvious workload imbalance between partitions, sometimes you may have to traverse multiple partitions to complete one embedding. This can go as high as number of the edges in the query graph, which is really bad. So the lesson here is neither data graph alone or query graph alone is enough to define what kind of workload distribution there is in the overall problem. To address this problem, we defined the notion of embedding cluster, which makes use of the both data graph and query graph information to form many small workload regions and work on the each regions independently. Let's see what embedding cluster is. So normally each embedding are unique to one another, but some part of them matches with the other embedding. For example, two embedding in the graph we have here shares B1 as a match for U1. Both of them uses B1 as a match of U1. Using this observation as a baseline, we define embedding cluster as the region of the graph which contains all the embeddings sharing the root node. Now, this construct can be applied to the other nodes as well, which we will apply in the iterative workload balancing. But for simplicity, right now we just consider the root node. So this kind of becomes one embedding cluster. So all the embedding that matches B1 to U1 lies on this region. Similarly, I mean, if you descend from B2, you can consider this to be another embedding region. Now this is good. You can give one cluster to one worker, another cluster to another worker, and then ask them to work. But the obvious observation over here is there is a significant amount of overlapping between different regions. So you don't want to store them separately and then incur the exponential memory requirement. That is where CECI comes into play. So we design a global data structure called Compact Embedding CLuster Index, which basically formulates the data graph into group of embedding cluster. So it stores all embedding cluster as one global data structure, but it links the candidate to the candidates of previously matched node to make it possible to traverse through given embedding cluster without interfering with another thread. So here's a typical look of the data structure over here. The skeleton of CECI looks exactly like the query tree, and every node has set of candidates that has been linked to all the nodes that are earlier in the matching order and is connected to that node. Now there are a lot of the nodes that has been colored red. Those are basically false positives. Again, previous speaker has iterated the importance of the efficient filtering mechanism to remove all the false positives. We didn't explore much on the filtering area. We basically used the commonly accepted and then simple enough rules from the existing work to reduce the size of CECI to as low as possible. So basically doing forward and backward iteration on the BFS tree and employing the attribute filters like degree or label or neighborhood signature made the final CECI to be the one in the right. So now we have a CECI structure which contains all the embedding cluster. Multiple threads can go on the different cluster as they wish without interfering with one another. Let's move to the next issue. It's the verification overhead. Again, to recap the backtracking-based verification, for every query node U in the query graph, you have to get one potential candidate B, and then make sure that matches U by checking a lot of the edges that node forms to already matched node in the embedding. So this process is done individually. So every time you connect one node to the backtracking tree, you have to make sure it is valid. So that involves normally a couple of non-tree edge checking when you have a skeleton, when you have a spanning tree-like structure. And then the problem with non-tree edge checking, sometimes determining whether there is an edge between two nodes in a graph gets more and more expensive with increasing size of the graph, unless you use a sparse matrix representation of graph, which is not feasible in terms of the memory requirement. So the obvious goal here is we have to batch the candidate verification, and we have to make sure that edge checking overhead is as low as possible. Now, CECI takes care of the second point. CECI already stores all the candidates next to one another linked with already matched node. So that way we can get the candidates corresponding to each of our already matched node linked to the current node. So every edge will have one list. So at this point, we can utilize all those lists, do the set intersection, and then form one final candidate list. Now this final candidate list is already verified list, so we don't have to go to data graph to check the validity of edge at all. So by utilizing this technique, we got up to 2.5 times speed up over manual edge checking process involved in most of the existing work. Let's move to the last issue I'm going to address here, the workload imbalance. As I have already iterated, all the graph problem are naturally imbalanced due to power law nature of the graph, and subgraph matching is actually further skewed by the distribution of embedding throughout the graph. So we have to have a better workload balancing mechanism to solve this problem. Embedding clusters can help. As we have already noticed, it forms a lot of the embedding clusters, whose count is likely to be many, many more than the number of threads. That way, we can use the dynamic workload balancing mechanism to provide the embedding cluster to different threads on demand, and that makes the workload balancing really good as compared to the other mechanisms. But there is still one big problem, really big problem, and we call this extreme cluster. So extreme clusters are the embedding cluster which is really, really big, and they normally tend to dominate the overall runtime of the whole process. As an example, I have a graph over here. You can see there are two embedding clusters. Cluster 1 has only one embedding for a given query graph, and cluster 2 has like nine embeddings. So by looking at this, cluster 2 will always take 90% of the runtime, no matter how many threads you use. So we have to have a mechanism to divide cluster 2 into smaller clusters. So how do we do that? Cost function. We define a cost function called cardinality. So the cardinality is defined between a pair of query node and then data node. That basically means how many potential candidate can you get by matching given query node with the specific data node. If you compute the cardinality from the leaf nodes of the query tree and then use this formula to combine the cardinality of the children and then go over and over up to the root query node, the cardinality in the root basically estimates the maximum number of embedding you can get from the given embedding cluster. So we have a sample computation over here for the given data graph. So if you look at the last two columns of the last two rows of the table, the combination between U1 and B4 yields up to 9 candidates, and then combination between U1 and B1 yields only 1 candidate. So using this information, we can now detect that the cluster 2 is really big to work for a single worker, and we need to divide it into multiple embedding clusters. So that is exactly what we do on the next step. So if the expected cardinality of given embedding cluster is bigger than the average cardinality you expect per thread, multiplied by some user tunable threshold beta, then you divide the given cluster into subclusters. Like we have a figure over there. EC1 is really big, so we basically divide it into 4 subclusters. And then once you have all the clusters, verifying this condition, then you can sort the cluster from largest workload to smallest workload, just in case to smooth out the runtime at the end. Just to evaluate the effect of beta, the lower we go on the granularity, the better we get the workload imbalance, which is kind of intuitive. So it's not a surprise. So let's take a look at some of the experimental results. We chose 2 parallel implementation competitors. One is DualSim from SIGMOD 16, which basically does dual simulation by loading partial data graph at a time. And then we have a PSGL from SIGMOD 14 who do really aggressive expansion on each node. Then for sequential solution, we chose Turbo ISO from SIGMOD 13 and CFL Match from SIGMOD 16, which has been mentioned on the previous talk as well. And then boosted Turbo ISO from BLDB 15. We evaluated on a server with 28 core, 512 gigabyte memory, each running 2 hyperthreads. We have numbers from other experimental environment as well. If anyone is interested, please check the paper. For the data graph, we used both synthetic and then real data graphs. Node count goes up to 1.4 billion. Edge count goes up to 12.9 billion. Some of the graph has node label, like a random graph has a 100 randomly generated label, and then human graph has 90 labels on the node. Let's see the result. For common queries, we compare with DualSim and PSGL. In average, we are 34 times faster than PSGL and 6 times faster than DualSim. Most of the speed up comes from better workload balancing and better work distribution facilitated by CECI. And for larger query, we compare with the sequential solutions. CFL Match, the figure on the top right is speed up against CFL Match on random graph and human graph. As you can see, up to query node 50, we are slightly faster than CECI, faster than CFL Match. And the bottom right shows the speed up against Turbo ISO and boosted Turbo ISO, whose performance are of the same region. One last experiment, we tested the scalability with increasing number of threads. Up to 16 thread, we are almost linear, and then on 64, we are dropping a little bit more. That's because our server only has 28 core with 2 hyperthread running, so after 56, it's kind of redundant to put more threads. Overall, the scalability is really good, and the bigger the data graph is, the better the scalability are. Just to summarize, smart division of the workload helped a lot to speed up the process. Batch verification and load balancing were very beneficial. We outperformed the sequential as well as parallel implementation of the state-of-the-art solutions. And we have extended our work to distributed system as well. If anyone has questions, please feel free to ask. For future work, distributed work still consists of a certain amount of data redundancy, so reducing that would be some goal. And then parallel processing on really large queries is still a very challenging problem, so we look forward to extending to that. Thank you, and please, any question, please go ahead.
Thank you. Thank you very much. Thank you. So we have, yeah. Hello?
It's a pretty interesting talk. So going back to the time and space complexity of your main method, I believe it's the size of the query graph times the size of data graph,
right? Which
turns out to be pretty non-trivial. So I'm just wondering, how do you deal with this complexity in order not to boil down to the worst case scenario in practice?
So I actually have a number to back that claim. Potentially, you would need, let's look at the largest data graph we have, Yahoo graph, the second last column from right. The worst case memory requirement for these 5 query graph are inside the parentheses. As you can see, we're gonna need like 577 gigabyte to store the CECI for Yahoo graph while processing QZ4 and QZ5, which is really large. But with the filtering and the refinement, the memory requirement drops to 274 gigabyte and 290 gigabyte, which is a huge drop. And the complexity is not that bad if you look in the context of existing work, because it tends to go up to number of edges in data graph raised to number of edges in query graph. So it's a polynomial compared against exponential.
Okay, thank you.
Okay, so I have a very short question. In your experiment, what's the size of query graph?
We have a 5 query graph over here.
Yeah.
So for parallel
Okay, so
solution, these are the query graph, QZ1 to QZ5.
okay, all right.
For the sequential, we have a query graph size from 3 to 50. So
Okay.
these are node size.
Yeah.
Edge can be different based on the traversal you do on the data graph.
All right, thank you very much. Let's quickly move to the fourth talk. So